So the last topic we're going to talk about in just plain magnetism are two laws. Before we talk about Gauss's law for magnetism, I want to remind you about Gauss's original law. So the thing we learned way back in January was Gauss's law, and you might put in parentheses for electricity, and it was written like this. So a couple things to remind you of here. So this whole side of the equation is the electric flux. And we used the symbol, I believe, where is it on here? I don't think we have the E on there. But now that we're talking about magnetism, it makes sense to have an E for this is electric flux. So the flux through a surface, if it's a closed surface, that's where there's the circle on this integral and an S. So the flux through a 3D surface depended only on the charge enclosed by that surface. So the electric flux was approximately equal to the net number of field lines through the surface, like punched through it. So if we do a drawing of that, remember if we had a positive charge, you know that the electric field around it, I've been using green lately for electric fields. So the electric field everywhere around a positive charge points away from it. Because the information that the electric field carries is, hey, there's a positive charge back there, so if you're positive, go away from it. If you're negative, come towards it. You go opposite these lines, but that's the electric field. So if I wanted to calculate something about the electric field or the electric flux, I would need to draw a three-dimensional surface, a closed three-dimensional surface. So this is a sphere. This is not a circle, because these lines are not only in the plane of the page, they point out of the page, they point into page, they point three-dimensional. So this is a three-dimensional offset sphere, and it's a closed three-dimensional object. So we use this, for instance, in this equation, Q enclosed over epsilon naught. Because this is an equal distance, that's an equal strength everywhere. So we could pull E out of the integral, and then the integral of the derivative of something is itself. So E times A equals Q over epsilon naught. Well, the surface area of a sphere, the area of this shape, is 4 pi r squared. And there's little q inside. I should have changed that. Little q inside over epsilon naught. And so we ended up with E equals 1 over 4 pi epsilon naught q over r squared. So I divided by this term, and then I just separated. I put all the constants in the front, and put the r squared over there. So remember, this was our k constant. So this is E equals, for a point charge, kq over r squared. So you knew that equation. You knew that equation from Coulomb's law, but we used this before to do with Gauss's law. I want to go back to Q enclosed. So if we had two charges, a positive and a negative, and let's make them equal. So when I draw the electric field, it would look like this. So now if I draw a sphere, pretend that's a sphere and not an oval. Actually, it doesn't really matter. I can see that Q enclosed equals 0. Why is it not on the screen? I thought I meant to paper it. Sorry. Because inside this red sphere, I have two charges. They're equal in magnitude. They're opposite in sign. Positive 3 plus negative 3 adds up to 0. There's no charge enclosed. And then if I look at the flux, well, this line goes out, but then it comes back in over here. This one goes out, it comes back in over here. These two never even intersect the surface. So every field line would either, like even this one that goes straight away, well, there's one over here that matches up with it. So the same number of lines leave that enter, so the flux is 0. The charge enclosed is 0. So this holds 0 on either side of the equation. Now we're going to use that same idea and apply it to magnetism. So Gauss's law for magnetism looks really similar. We're again going to have a closed surface integral, but now we're going to do magnetic field dotted with the area, but this is equal to 0. Because for me to set up an electric field, I need to, to set up a magnetic field, I can do it with a permanent magnet, I can do it with a current carrying wire. Let's do a permanent magnet first. So if I have a permanent magnet, north and south, and we've mentioned this a little bit, but it hasn't been a big thing, the electric field around it points from north to south. So away from north towards south. And you could fill more lines in there. So if I draw, again, this is a sphere, because these would all be three-dimensional magnetic field lines. Even some that are bigger, they go out and come back in, or they're enclosed completely. So the magnetic flux through the surface of this sphere is 0. Now you could say, well, don't draw it that big. Let's just draw it around this area. That looks like we just have an outward. Well, but the thing is, if you zoom in on a magnet, another way of saying it is if you break a magnet, into two pieces, so let's say this is the break of that previous magnet, original north-south, this is the south, this is the north, and they would actually attract each other to hold stronger here. And if you break it again, you're going to get a north and a south and a north and a south. And if you break it again, you're going to get a north and a south, and you're going to get a north and a south. And even when you go microscopic, you're going to have a north and a south and a north and a south. So no matter how small a sphere you enclose about something, you always have both poles. The correct language for this, I'm going to say it differently. We have never found magnetic monopoles. If I could spell it right, poles. Mono, means one. We have never found just a north isolated or just a south isolated. A different way of thinking about this is if you have like a long straight wire, if this is carrying current to the right, you know that it's making circular magnetic fields around it, and they're coming out of the page on this side, and they're going into the page on this side. Each of these circles, I drew one too many, so let me match them up. So if I draw a box around this wire, I would always have some coming out and some coming back in. Draw a smaller box, out and in. Smaller box, out and in. There's no such thing as a magnetic monopole. Now, physicists don't like that. We actually want there to exist magnetic monopoles, because when we start putting the 4 of Maxwell's laws together, this is one of the ones that we don't like being 0. We wish there was something in here that was magnetic poles enclosed, but they don't exist as far as we have found. Doesn't mean they couldn't, but it means if they do, they're really hard to find. Pretty much whenever you have any magnetic field, there's an in and an out. There's a north and a south. So it seems, so why even bring it up? Well, because we're building up to Maxwell's laws. But you'll never use this for a calculation because it's always true, but it's not really helpful, except in some really special circumstances. But remember, that was true with the original Gauss's law. Always true, only sometimes useful, like really symmetric situations. Like it was useful here. We could find the electric field. Here we can't, because that's not a uniform electric field. We can't separate it. We can just find the flux, and we know that flux is 0. So there is one more equation we're going to talk about that actually is useful, and it's both useful in physics and it will be useful for you on the AP exam, and that is Ampere's law. So Ampere's law is similar. Let me write it first. So the first thing I want you to notice is that here, let me put Gauss's law for electricity back up here. E dot dA equals Q enclosed over epsilon naught. Okay, so we replaced electric with magnetic. But this is around a curve, a closed curve. So this is a 2D surface. 2D surface, not a 3D. This was 3D. So, and this is the length of that curve. Often, these would be circles, could be a rectangle, but a two-dimensional surface. And then, that magnetic field strength only depends on how much charge goes through, bad teacher, how much current goes through that 2D surface. Notice we also have our new constant, and besides switching constant, it also switches location. It's multiplied instead of divide by. That's an observed fact. So to give you an example of this, I'm going to draw current to the right. And then I am going to draw a 2D surface around it. So this is a circle, not a sphere like before. This is a circle, and I'm trying to draw it on edge. See, a little 3D. So it's actually, the circle is actually perpendicular to the page. So it's drawn at a distance. I don't know why I did that one in red. It's drawn at a distance R from this wire. So this is useful because now I can apply Ampere's law. I have current going through this circle. So B dot dl equals mu naught I enclosed. I am at the same distance all the way around, so it's the same strength magnetic field, so I can pull that out of the integral. And then the integral of the derivative of the length is just equal to the length. And then mu naught, and the I that goes through the circle, that punches straight through the middle. That's just the I in the problem. Now the length of a circle is its circumference. And remember, circumference is 2 pi r. And so I can finish this equation right here. Ampere's law is on the College Board formula chart. The magnetic field equation that I told you about a couple of days ago for a long straight wire is not on the formula chart, but you can get it really quickly from Ampere's law. And that's where the 2 pi comes from, because it's the length of the circle that we drew. So length of the circle is the circumference. Now, the solenoid equation, that is on the formula chart, mu naught n I. So you don't have to rederive that one. It's given on the formula chart. But the one for the long straight wire is not. You have to think through the 2 steps to get it from Ampere's law. So if we had a second current running through the same circuit the opposite direction, the currents would cancel out, but that also makes sense. We'd have a magnetic field going this way, we'd have a magnetic field going this way. They cancel each other out. If the current was outside the circle, well, then there'd be some field here and some field here made by this one, but overall on this surface when I drew it, the overall would be 0 because they cancel out in the 2 different places, all the way around the whole circle. Because remember, again, it's every point in space. This is not 2 points. This is perpendicular, a circle perpendicular to the paper. So Ampere's law, really useful, and even useful for the College Board formula chart. And that's it for this unit. And then we have one more unit where we put everything together in electromagnetism.